Well, welcome back to College Physics 1. We're now going to be doing our third lecture in this course. And just as a little bit of a review, um, we're breaking the material in our textbook into two parts. College Physics 1 will be topics 1 through 15. And just as a reminder, College Physics by Survey is our textbook. And right now we're working through the mechanics section. So our first week, we started to talk about units, giving that some perspective, talking about mass, talking about length, talking about time, and then giving some basics of how we can be approaching our analysis with trigonometry, geometry, and algebra. So we did that. And we started to look at vectors. And then last week we looked at motion in one dimension, and we developed some propositions on how that would work for one dimension. Now we're going to go into two dimensions, and that's going to be the focus of today. So now instead of just going in one direction, we can be thinking about two directions. We're not talking about three directions, but at least in a two-dimensional space, that's what we're focusing on today. And just as a reminder, you've probably seen this, that the material is broken into several sections. We have some reading questions. We have a lot of the technical details for the chapter. We have a summary questions at the end that you can start to be thinking through that. And then there's a summary. And so those are the four things that we'll cover this week. For some of the material, we may actually pick up the pace and just kind of go through it at a high level, the summary questions at the end, for example. So we'll go ahead and cover these because these tend to be a little bit higher level, but also giving us some perspective on some of the material. And so if you've read the material from this chapter beforehand, hopefully this will make it a little bit easier for you to understand the material and these questions. So a book is moved once around the perimeter of a tabletop with the dimensions of 1 meter times 2 meters. If the book ends up at its original position, what is the displacement and what is the distance traveled? And so this is where you get this interesting set of thoughts. Remember, of displacement versus the distance traveled. These are two different parameters. And so we're talking in two dimensions. And so the displacement, since it's back to its original position, is 0. But since it's traveled the dimensions of this table, and we know what the dimensions of the table are, we can figure out what that is. So hopefully that's fairly straightforward. So we talked about a vector before. So a vector lies in the XY plane. So we're talking in two dimensions. For what orientation would both components be negative? And so this is where we're starting to think about, we have a coordinate system, an X and Y coordinate system, and we can be thinking about when that would be the case when both the X and the Y would be negative. So what this would say is it lies between 180 and 270 from the X-axis. That was when we would see that taking place. And anyway, I think if you were just to put down a graph, an X and a Y, an X and a Y, what they're talking about is both X and the Y has to be negative. And so it has to be this quadrant where they're both negative is what they're trying to convey. So for this question, which of the following quantities, if any, remains constant as a projectile moves through its parabolic trajectory? And so the answer to this is 2 and 3. So acceleration and the horizontal component of velocity. That's what they're claiming would be the case for a projectile moving in a parabolic trajectory. So, and then for this question, a sailor drops a wrench from the top of a sailboard mast while the boat is moving steadily and rapidly in a straight line. Where will the wrench hit the deck? And so this is interesting. We're having motion of the ship that and then you have to figure out how that's going to affect the what it would impact the movement of that wrench. Well, at the point when it's dropped, the wrench is actually moving at the same rate as a sailboat. And so that's why it would say that it would fall at the bottom of the mast. Something for you to think about. Okay, now we'll start to get into two-dimensional vector analysis, and we started to look at this a little bit here. So as a projectile is thrown upward at a non-vertical angle, so it's moved at some type of angle here, and it moves in a parabolic path, and we talked about a parabolic path before in the previous charts. At what point along the path are the velocity and the acceleration vector for the projectile parallel to each other? And so you can think about that for a little bit. And so basically what it's saying, the answer is nowhere. Nowhere is the acceleration and the velocity vectors the same. You may want to review and think about what exactly acceleration means. What is zero acceleration? What is positive and negative acceleration? And maybe that'll help you get a perspective on that a little bit better. Okay, with that, we'll move into our topic discussion. And coming up to this point, our study of motion has involved the concept of displacement, velocity, and acceleration in one dimension. That's what we talked about in our last lecture. In this new topic, we'll extend these concepts by applying vector techniques to studying two-dimensional motion, including projectiles and relative motion. So we're now getting the tools to do something in a little bit more complicated scenarios. So in the figure, we have an object moving along some curved path between P and Q, and the displacement vector delta R is the difference between the position vectors. So delta R is RF minus RI. And so here is what we're seeing is that difference. And so we have some kind of path, and we see these 2 points where we get some kind of displacement. So in one-dimensional motion, the direction of vector quantities such as a velocity or acceleration can be taken into account by a plus or a minus sign. For example, the velocity of a rocket in a positive is positive if the rocket is going up and negative if it is going down. When working in 2 or 3 dimensions, we need the concept of vectors. So looking at the figure, which shows an object moving through space when the object is at some point P at time Ti, the position is described by the position vector Ri. So here we have that R sub I drawn from the original point P. When the object is moved to some other point Q, at that point Tf, the position vector is R. From the vector diagram, you can see that the final position vector is a sum of the initial position vector and the displacement. From this, we can conclude that the object's displacement is defined as this change in the position vector. So moving on here. So in this figure, the displacement vector has components delta x and delta y. And so we see 2 different components, and we're breaking it up into the coordinate system that we have, an x and a y. And so that's what we have. And so the displacement vector's components delta x and delta y shown in the figure for an object that moves from a location, the initial location to the final location in a time interval of delta t. And so the x component of the object displacement is delta x right there, and the y component is delta y. So let's generalize the definitions of velocity and acceleration we covered in topic 2. And so an object's average velocity during a time interval delta t is its displacement divided by delta t. Okay, because the displacement is a vector quantity and the time interval is a scalar quantity, we conclude that the average velocity is a vector quantity directed along delta r. The x and y components of the average velocity are given by the equation shown, and express the rate at which the object's position is changing along the x and y axis respectively. Note that the magnitude of the average velocity is just the distance between the endpoints divided by the elapsed time. An object's instantaneous velocity, v, is a limit of the average velocity as delta t goes to 0. So here we have the average, we have the instantaneous, and so hopefully this is giving you some perspective of we have the going in each of those directions. So we're breaking it into components based on the coordinate system that we're leveraging. And then moving on, an object's average acceleration during a time interval delta t is a change in the velocity of delta v divided by delta t. Average acceleration as components given by the equation shown were v sub x and v sub y, and then x and y components of the velocity vector. An object's instantaneous acceleration vector a is a limit of the average acceleration vector as delta t goes to 0. And so you should be aware that the object can accelerate in several ways. The magnitude of the velocity vector, which is the speed, may change with time, so it may not just be going in a constant speed. The direction of the velocity vector may change with time, even though the speed is constant. This can happen along a curved path. So both the magnitude and the direction of the velocity vector may change at the same time. So all these are possibilities. And so the focus here was we're trying to think about average. Sometimes even if it's not perfectly accurate because it's maybe not going along a straight line per se, as we saw with this figure, some of these previous figures here, that you may be just capturing along 2 points, but that may be adequate for what you're trying to accomplish at this point. So let's have a question to be thinking about this. So which of the following objects can't be accelerating? An object moving with a constant speed, an object moving with a constant velocity, an object moving along a curve. So basically it's here, an object moving with a constant velocity. That's what we wanted to be pointing out. If velocity is constant, the acceleration, that is the rate of change in velocity, is 0. So therefore it's not accelerating. An object may have constant speed, but still be accelerating due to a change of direction of the velocity. If the object is following a curved path, it is accelerating because the velocity is changing in a direction. So that's just something for you to be thinking about. Okay, here's another one. Consider the following controls in an automobile: a gas pedal, a brake, steering wheel. The controls in the list that cause an acceleration in the car are, what do you think? And the answer is all of these. They're going to cause a different type of impact. If the velocity is constant, the acceleration is 0. An object may have constant speed, the magnitude of velocity, but still be accelerating due to change in the velocity. We already mentioned that if an object is following a curved path, it's accelerating because the velocity is changing in a direction. So all of that is true, but you can probably think about it. A gas pedal, that's going to vary. All of these can be impacting acceleration with the brake, the gas pedal. The steering wheel, you can be changing the direction of the vehicle. Maybe that's a controlled or maybe an uncontrolled possibility, but you can see how that would also have the ability to change the acceleration. Oh, okay, a girl on a bicycle takes 15 seconds to ride halfway around a circular track of radius 10 meters. What is a girl's average speed? So you can be thinking about this, that if using some geometry in this case, we know that the radius is 10 meters. We know that a semi-arc of a circle, what that is, that pi comes into that equation. So the average speed is the path length traveled divided by the time interval. In this case, the path length equals pi r, half the circumference of the circular path, with r equals 10. So her average speed is pi times r divided by delta t, which is pi times 10 divided by 15, which is 2.09 meters per second, approximately. Girls on a bicycle, once again, this is the same question. 15 seconds to ride around the circle or track. What is the magnitude of her average velocity? And so her, this is where we had this equation before. What is the average velocity? So if we just go back a couple charts here, here is the average velocity. Sorry, this is the average acceleration. So, and here is the average velocity. So going back to this question that we were just talking about. So it's basically delta R over delta T. And so that would be 2R over delta T. So that's 2 times 10 divided by 15, which is 1.33 meters per second. So think about that a little bit, and we'll continue to move on. So in the figure, a woman jogs along the dash path from A to B. So a diagonal across this field, you could say. So she does that in 20 seconds, a traveling path length of 30 meters plus 40 meters, 70 meters, and a distance of, let me see, traveling a path length of 30 meters and 40 meters. So we're given the dimensions of this path. And so the total distance would be here is 50 meters. So an average velocity is a vector equal to the displacement divided by the time interval, and depends only on the motion's endpoint and not on the actual path traveled between them. So the average speed is a scalar equal to the actual path length traveled, including any tracing of steps or deviation for the straight line divided by the elapsed time. The figure shows a woman jogging along a rectangular path of a small green space going from point A to point B in 20 seconds. The path length is 30 meters plus 40 meters equals a total of 70 meters. So our average speed equals the path length divided by the total time, which is 70 meters divided by 20 meters is 3.5 meters per second. The magnitude of our average velocity depends only on the distance between the endpoints, which is 50 meters. So then V equals D over, well, we have the equations here. So we have the path length, the average speed, and we can calculate the average speed and the average velocity. So I think I misspoke. So instead of doing the diagonal, she's actually going on the peripheral. So up, going in one direction and then up in the other direction. So sorry about that. So let's now come back to this parabolic trajectory. So here we have a figure of the parabolic trajectory of a particle that leaves the origin with a velocity of v sub 0. Note that v changes with time. However, the x component of the velocity x, the velocity v sub x, remains constant at time equal to its initial velocity. Also, v sub y equals 0 at the peak of the trajectory, so up at this top point. But the acceleration is always equal to the free fall acceleration, which acts vertically downward. So in this topic, we look at objects that are moving in both the x and y directions simultaneously under constant acceleration. An important special case of the two-dimensional motion is called projectile motion. Anyone has tossed any kind of object into the air has observed projectile motion. If the effects of air resistance and the rotation of the Earth are neglected, the path of a projectile in Earth's gravity field is curved in the shape of a parabola, as shown in the figure. The positive x direction is horizontal, and the right and to the right, and the y direction is the vertical and upward, positive upward. The most important experimental fact about projectile motion in two dimensions is the horizontal and vertical motions are completely independent of each other. This means that no motion in one direction has any effect on the motion in the other direction. So you can imagine tossing a baseball along a path showing in the figure. The motion in the y direction will look just like the ball tossed straight up under the influence of gravity. So interesting, we can be treating x and y motion completely separately. So here is the impact of the launch angle. And so you can see a projectile launch from the origin with an initial speed of 50 meters per second at various angles. So maybe you can think of any number of things. You can think of baseball, and so, or do they pop it up and so it lands in the infield? Or do they get it just at the right angle? So maybe a 45 degree and it's a home run. And maybe this is out in one of the left or right field or center field. And so you can see those variations and how that might look. You can be thinking about other type of experiences, but maybe that's one thing that you guys would be familiar with. Now let's look at an example of a gun that is firing a projectile. Okay, so a ball is fired at a target at the same instance the target is released. Both fall vertically at the same rate and collide. This figure shows an experiment illustrating the independence of horizontal and vertical motion. The gun is aimed directly at the target ball and fired at the instant the target is released. In the absence of gravity, the projectile would hit the target because the target wouldn't move. However, the projectile still hits the target in the presence of gravity. That means that the projectile is falling through the same vertical displacement as the target displaced is despite its horizontal motion. So you can see that they're both going down at 9.8 meters per second. And so there's still a collision is what it's trying to point out here in that illustration. So this is a picture of a multi-flash photograph of the projectile target demonstration. The gun is aimed directly at the target and is fired at the same instance the target begins to fall. The projectiles will hit the target. The experiment also works when set up as an image shown where the initial velocity has a vertical component. So you could actually aim it up and still get the same kind of experience, and it hits and you have the evidence of it hitting at a certain location. So in general, our equation of constant acceleration follows separately for both the x direction and the y direction. Notice that the initial velocity has two components. So let's assume that at time 0, the projectile leaves the origin with an initial velocity of v sub 0. Okay, v sub 0 here. If the velocity vector makes an angle theta 0 with the origin, where theta 0 is called the projection angle, then from the definitions of the cosine and sine functions in the figure shown, we can write these equations where v sub 0x is the initial velocity, and in the x direction, and v sub 0y is the initial velocity in the x direction. So we're doing this decomposition into the coordinate system, v sub x, v sub y, and then we can do this for each point along the way, and using the equations we have already derived using trigonometry, we can easily figure those out from v sub 0 as long as we know this angle. So our equations for motion with constant acceleration in one dimension carry over to the two-dimensional case. There is just one set of 3 equations for each direction, as you can see here. And so now we have these equations that we're building on what we already had, and we're just adding a little bit more. So we have in the x direction and the y direction. And just as a reminder, some of these other values relating v sub y and v sub x, and how we can put x and y together and come up with the initial v. So anyway, so we have more information there that I think is useful as we move into a two-dimensional scenario. So let's write the kinematic equations for the case of projectiles close to the Earth's surface with friction, when friction is negligible. Notice that the acceleration in the x direction is 0 because air resistance is neglected. This means that a sub x equals 0 and the projectile velocity component along the x direction remains constant. If the initial value of the velocity component in the x direction is v sub 0 x equals v sub 0 cosine theta 0, then this is also the value of v sub x at any later time. The horizontal displacement can be written as shown. So here is just another scenario for these kinematic equations, given that given that initial condition. So let's take a question and kind of go over what we spoke about. So let's summarize the important facts about projectiles. One, provided air resistance is negligible, the horizontal component of the velocity v sub x remains constant because there is no horizontal component of acceleration. The vertical component of the acceleration is equal to the free fall acceleration minus g. So that's the gravity that we know on Earth is 9.8 meters per second. The velocity component of the vertical component of the velocity and the displacement in the y direction are identical to those of a free falling body. Okay. And then finally, projectile motion can be described as a superposition of two independent motions in the x and y direction. So thinking about that, let's just have a question where we could contemplate this. And so suppose we are carrying a ball and running at constant speed and wish to throw the ball and catch it as it comes down again. And so you should what? What do you guys think would be the answer here? So the answer is throw the ball straight up in the air and maintain the same speed. So that's number 3 as shown here. So the reasoning is a projectile has constant horizontal velocity. Thus, if the runner throws the ball straight up into the air, the ball maintains the horizontal velocity it has before it was thrown. If the runner's frame of reference, the ball appears to be going straight up and coming straight downward. To a stationary observer, the ball follows a parabolic trajectory, moving with the same horizontal velocity as the runner and staying above the runner's hand. So some interesting things that we're beginning to see is this frame of reference. And I think that would be a useful thing for you to be thinking about as we go forward. So here's another question. As a projectile moves in a parabolic path, the velocity and acceleration vectors are perpendicular to each other. And so what do you think, when would that occur? And so the answer is at the peak of its path. And the reason is that the velocity is always tangential to the path while the acceleration is always directly vertical downward. Thus, the velocity and acceleration are perpendicular only when the path is horizontal. This can only occur at the peak of the path. And we began to talk about that in our last lecture, if you might want to remember that. So let's talk about the problem-solving strategy. And I find that these little short synopses are useful. And these are maybe some slides or things in the textbook you might want to remember. So first, select a coordinate system. That's important. So, and sketch the path of a projectile, including initial and final positions, velocities, and accelerations. And of course, you want to make that coordinate system so it's convenient for you. And so then you can draw the projectile path. Second is you want to resolve the initial velocity vector into x and y components. 3, you treat the horizontal component and the horizontal motion and the vertical motion independently. And we've seen how we could do that sometimes one or the other is very straightforward. And then you want to follow the techniques for solving problems with constant velocity to analyze the horizontal motion of the projectile. Finally, follow this technique for solving problems with constant acceleration to analyze the vertical motion of the projectile. So now we have another scenario of problems. This is for projectile motion that we have a nice little path of how we could go about solving those. So here is an example when we get into relative velocity. The position of car A relative to car B can be found by vector subtraction. The rate of change of the resultant vectors with respect to time is a relative velocity equation. So we see this coordinate system we've created, and relative velocity is all about relating the measurements of two different observers, one moving with respect to the other. The measured velocity of an object depends on the velocity of the observer with respect to the object. Think about driving on a highway, for example. Cars moving in the same direction are often moving at high speed relative to Earth, but relative to each other, they are hardly moving at all. To an observer at rest on the road, a car might be traveling at 60 miles per hour, but to an observer in the truck traveling in the same direction at 50 miles an hour, the car would appear to be traveling only 10 miles per hour. So measurement of velocity depends on the reference frame of the observer. Reference frames are just coordinate system. Most of the time we use a stationary frame of reference relative to Earth, but occasionally we use a moving frame of reference associated with a bus, car, or plane moving with constant velocity relative to the Earth. In two dimensions, relative velocity calculations can be confusing, so we will use a systematic approach. Look at the figure. Okay, E is the observer's assumed stationary with respect to the Earth. So we see that over here. The two cars are labeled A and B. R sub A E is a position of car A as measured by E in a coordinate system fixed with respect to Earth, and R sub B E is a position of the car B as measured by E. And R A B is the position of car A as measured by the observer in car B. For this notation, the first letter tells us what the vector is pointing at, and the second letter tells us where the position vector starts. So the position vector of car A and car B relative to E is R sub AE and R sub BE, and given in the figure, and those are given in the figure. So how do we figure out R sub AB, the position of car A as measured by observer in car B? We simply draw an arrow pointing from car B to car A, which can be obtained by subtracting R sub BE from R sub AE. So this is what we're trying to come up with. Now the rate of change of these quantities with time gives us a relationship between the associated velocities. The coordinate systems of observer E doesn't have to be fixed to Earth, although it often is. Take careful note of the pattern of subscripts. Also be aware that the equation doesn't work for observers traveling a sizable fraction of the speed of light when Einstein's theory of special relativity comes into play. So we're talking about Newtonian mechanics, not Einstein and special relativity. So we can just forget about that for now. That won't come until later, and really getting into the second semester of going over this material. So here is a strategy you can use when solving relative velocity problems. And so this first one maybe is starting to sound familiar. You want to write it down. You want to label the objects. You want to have a coordinate system. And so, in the previous figure, we were using E to represent Earth or some kind of a fixed position on Earth. And so that's the first thing. So we label the objects. So the second thing is we write the relative velocities. Look through the problem for phrases such as the velocity of A relative to B, and write the velocity as V sub AB. when the velocity is mentioned, but it isn't explicitly stated as relative something that's almost always relative to Earth. So and then you want to take the three velocities you found and assemble them into an equation similar to the one shown. Okay, here is what we're getting a chance to put that all together with subscripts in an analogous order. There will be two unknowns components, solving for them with the x and y component of the equation developed in step 3. So that's the approach for how we do relative velocity. It's just a little bit more complicated than what we talked about previously of projectile motion. And let's continue on as we develop these things here. So, so here's a whole bunch of things here that we want to consider the following situations, a whole bunch of things, and maybe you might want to think about, is there something in common between these? And so what we're trying to do is to introduce the concept of acceleration, exploring pre-existing definitions of the term and in contrast everyday usage of the word with the way physicists use it. So in how many of the situations is the object accelerating? So I know that this is an example. The moon is constantly accelerating towards the Earth, but there's other forces that keep it in an orbit going around the Earth. So maybe that's one that you're not familiar with. A molecule on the floor of the room, maybe you might want to think about that. Some of you with some biology, that's where you're at. That might make a little bit more sense. A vibrating string, you can think about that. And we'll just continue on. So a pendulum is released from the point at position A and swings towards the vertical under the influence of gravity. It's depicted below. When at position B, which direction most nearly corresponds to the direction of the acceleration? So basically it's here, okay. So what we're trying to do is to develop an understanding of the vector nature of acceleration in a curvilinear motion, as what we would see in a pendulum. And so acceleration is the rate of change of velocity. If an object's speed is changing, that means that the length of its velocity vector is changing. So the acceleration must have a non-zero component parallel to the velocity vector. If an object's direction of motion is changing, that means that the direction of the velocity vector is changing. So the acceleration must have a non-zero component perpendicular to the velocity vector. At point V, the pendulum bob is both speeding up and changing direction. So this is what we're pointing out here. At that moment in velocity, its velocity points in the direction tangential to the circular path it's following direction. So since it is speeding up, the acceleration must have a component that points in the direction 3. Since it is traveling in a curved path, it must have an acceleration component that points towards the center of the circle, the so-called centripetal acceleration, which is in direction 1. Thus, the acceleration vector must point somewhere between the direction 1 and 3. To find the exact direction, we would have to calculate the relative sizes of these two components of the acceleration. So some key things to take away from this is acceleration is a vector that describes the rate of change of the velocity vector's magnitude and its direction. It is often useful to divide the acceleration into components that are parallel, tangential, and perpendicular to the object's direction of motion. A non-zero tangential component of an acceleration indicates that the object is changing speed. A non-zero perpendicular component of the acceleration indicates that the object is changing direction. So anyway, we'll just leave that and then move on to some topic summary points here. And so we've now moved from one dimension into 2 dimensions. And so basically Instead of just having a single direction, we have these vectors, and vectors can be broken into components into multiple directions. That's what we're starting to see as a result of that. The average velocity of an object during the time interval delta t is shown here. Taken to the limit, the expression as delta t gets arbitrarily small gives us an instantaneous velocity v. The direction of the instantaneous velocity vector along the line that is tangential to a path of the object and in the direction of the motion. The average acceleration of an object with a velocity changing by delta v as a time interval delta t is shown. This takes the limit of the expression as delta t gets arbitrarily small. It gives the instantaneous acceleration a. And so that's what we have here, giving a nice summary. So we have these two-dimensional motion. So the general kinematic equations in 2 dimensions for object with constant acceleration or for the x and y direction are given here. The speed of v of the object at any instance can be calculated from the components of the velocity at the instant using the Pythagorean blah. Anyway, you can be using geometry to help you out with that. And the angle that the velocity vector makes with the x-axis can be found by taking the reverse tangent. So Pythagorean, anyway, using this equation here. Moving on. So just finishing up with a few more concepts. The horizontal and vertical motions of a projectile are completely independent of each other. So you can break that up into components, and there's times when that can be quite useful. If you have motion in one direction, then the other one is just going to be unaffected by that. And so the kinematic equations are easily adapted and simplified for projectiles close to the surface of the Earth. The equations for the motion in the horizontal or x direction and the vertical or the y direction are shown here. Problems are solved by algebraically manipulating one or more of these equations, which often reduces the system to 2 equations and 2 unknowns. And then finally, we talked about a relative motion. So here, let E be an observer, okay? And B is a second observer traveling with velocity B sub BE as measured by E, as shown in the figure. If E measures the velocity of an object A as V sub AE, then B will measure its velocity as V sub AB, which is equal to V sub AE minus V sub BE. The relative velocity equation can be derived from the figure by dividing the relative positions equal the relative position equation by the delta t and taking the limit as delta t goes to 0. Solving relative velocity problems involve identifying the velocities properly and label them correctly, substituting into the equation, then solving for the unknown quantities. Okay, that's going to be it for this lecture. Thank you very much.